Welcome back. In the last video, we proved an important theorem about fixed fields for a bunch of homomorphisms, okay, from one field to another field. So, if sigma 1 through sigma n are homomorphisms, distinct homomorphisms from K to L, and F is the fixed field, then the degree of K over F is at least n. So, we are now going to prove the second important theorem about fixed fields that I mentioned last time. So, let me write the theorem here and we will prove it in the next slide. So, let now K be any field, okay, and let sigma 1 through sigma n be field automorphisms. Remember, I used the word automorphism last time. Automorphism is simply an isomorphism from K to K, okay. So, let these be distinct field automorphisms. So, let me put that here because that's important. I need to take only different ones. Distinct field automorphisms. If F is their fixed field, that means F is the sorry, I am not omitting the main hypothesis. Suppose that sigma 1 through sigma n forms a group. So, this is the crucial additional hypothesis, forms a group under composition. So, in the language of Galois groups, here of course I am not starting with a field extension. So, I can't talk about Galois group, but suppose you did, and all these sigma i's are automorphisms over that base field, then the hypothesis that they form a group is simply the hypothesis that this is a subgroup of that Galois group. I am not fixing a base field, so I do not want to talk about Galois group here. Suppose that this set forms a group under composition. Now, if F is the fixed field of these n automorphisms, then K colon F, this is the equality. So, K colon F is equal to n. So, we remark that by the first theorem. So, think of this as theorem 2, okay, theorem 2 about fixed fields. By the first theorem, we have K colon F is at least n. So, we have now to show that it cannot be strictly more than n, and we also know in general it can happen that K colon F is strictly bigger than n, but this theorem says if is a group, so this is a new hypothesis, then equality must hold. So, K colon F is always at least n, and it can be strict, as I told you last time. If you take the field Q adjoint root 2 comma I and take 3 automorphisms, 3 homomorphisms or automorphisms actually in that case, identity sigma 1 sigma 2, the fixed field has degree 4, whereas there are only 3 automorphisms, but there they do not form a group, okay, because sigma 1 sigma 2 is not in that set. So, if they form a group, then K colon F is n. So, as we prove this, we will note where we are using the hypothesis about group. That this forms a group. I mean, we have, let us note just for fun where we are explicitly using that hypothesis, because without that hypothesis, the statement is false, as that example shows. Okay. So, let me start the proof. Let me also remark a priori that the proof is actually just linear algebra. It is exactly like theorem 1, except that it is slightly more involved, but it is still elementary linear algebra. So, I will try to go slowly and try to cover all the facts, but you might want to carefully do this, follow this on your own, and if needed, go over the video again or ask questions in the forum. The best way to understand these kind of things is to work it out yourself. So read listen to what I'm saying, but pause it if needed and work it out on your own. Okay, so let R be the index. Actually I'm not going to give it a name because I don't need to. So suppose for a contradiction that k colon f is strictly more than n, because we know it is at least n and we are trying to show that it is equal to n, we are required to do anything only if k colon f is strictly more than n. Then let or choose n1 independent elements. So alpha 1 through alpha n plus 1 over elements in k which are linearly independent over f. This is basic linear algebra, right? You have k is a vector space over f, its dimension is strictly more than n, which is to say that there are n plus 1, at least n plus 1 linearly independent elements. Maybe the dimension is n plus 3, I don't care. It's at least n plus 1. So I can take n plus 1 linearly independent elements. Now, just like in the previous theorem, we are going to cleverly consider a homogeneous system of equations. Consider the following homogeneous system of equations, of linear equations with coefficients again in this case the L is also k, so coefficients in k. And what is this equation? So here it is a homogeneous system of equations. So as I remarked earlier, these two are brilliant proofs. Okay, so this is part of the beauty of the whole subject. So please make sure that you understand this and enjoy the proofs as much as I do, because this is really wonderful. So what is the linear system that I want to consider? See, earlier, if you just go back to the proof, I looked at this system where I fixed alpha 1 in the first row, alpha 2 in the second row, alpha r in the rth row, and I fixed sigma 1 in the first column, sigma 2 in the second column, sigma n in the last column. Here I am going to fix sigma 1 in the first row. So the equation, the system is sigma 1 alpha 1, sigma 1 alpha 2, sigma 1 alpha n plus 1. And second row will deal with sigma 2 alpha 1, sigma 2 alpha 2, sigma 2 alpha n plus 1. So I am fixing sigma is in the rows now as opposed to columns in the previous theorem. And the last row will be sigma n alpha 1, sigma n alpha 2, sigma n alpha n plus 1. Okay, so alpha i's are fixed in the column. So alpha 1 takes care of the first column, alpha 2 takes care of the second column, alpha n plus 1 takes care of the last column. Sigma 1 is the first, sigma 2 is the first row, sigma 2 is the second row, and so on. So the system is this. Okay. So now what is the size of this matrix? This is, there are n rows and n plus 1 columns, right? This is an n by n plus 1 matrix with entries in k, of course. So in terms of equations and variables, there are n equations, n plus 1 variables. So again, number of equations, just like in the previous case, is strictly less than number of variables. Remember, here our supposition is that opposite of what we supposed in the previous theorem. There we assume that k colon f is strictly less than n, and by arranging the matrix in a clever way, we got number of equations less than number of variables there. Here we are assuming the opposite, k colon f is strictly more than n. That means there are more alphas than sigmas, but then by transposing the matrix, we still have this hypothesis that the number of equations is strictly less than the number of variables. So hence, so I am just separating this. So hence, there is a non-trivial solution. So there are non-trivial solutions. There is at least one non-trivial solution. Now here is where we have to be, this is, as I said, this proof is a little more tricky than the previous one. So I am not going to pick any arbitrary non-trivial solution, but I am going to choose a non-trivial solution of the following type. Choose a non-trivial solution beta 1, okay, so non-trivial solution with the least number of non-zero coordinates. What do I mean by this? So I am going to choose a non-trivial solution and I am going to see, I am completely okay with rearranging the variables. That means I am completely okay with the order of alpha i's is irrelevant here. So I am going to rearrange, so take any non-zero solution and rearrange the variables in such a way that the last few, the tail of this solution is zeros. So least number of non-zero coordinates. So here beta 1 through beta r are all non-zero. And there is, so that is the first statement, and there is no non-zero or non-trivial solution with fewer than r non-zero entries. Okay, so remember that there is a non-zero solution means one of the coordinates is non-zero. So of course r is greater than equal to 1. So I am only interested in non-trivial solutions. That means at least one entry is non-zero. So I take, maybe there is an entry with, if n is 5, each solution will have 6 entries, right? Because these are n, sorry, here I have n plus 1, so which I should, okay. So there are n plus 1 entries in the solutions. Maybe there is one with 5 non-zero zeros, non-zero coordinates. There is another solution with 6 non-zero coordinates. There is one with 3 non-zero coordinates. So I pick the least number of non-zero coordinates. So if there is 3, if it is 3, then there will be beta 1, beta 2, beta 3 followed by zeros, and there is no solution with 1 or 2 non-zero entries. Okay, so that's what I mean. So this is the first conceptual point that you have to understand. So I pick among all non-trivial solutions the one with the least number of non-zero coordinates. Remember, the number of non-zero coordinates is a number between 1, it can be 1, 2 up to n plus 1. Maybe there is no non-zero solution, I mean maybe every non-zero solution has all the entries non-zero, in which case r is n plus 1. But maybe there is a solution with one non-zero entry, one zero entry, all others non-zeros, in which case I take the r to be n and so on. So I don't care what it is, but I take r, r is a number between 1 and n plus 1, and I am choosing a particular solution which has the exact number of non-zero entries. So we will first quickly dispose of the case that r equal to 1. If r equal to 1, then that means you have beta 1 equal to 0, non-zero, beta 2 and beta 3 up to beta n plus 1 are all zeros. So this of course is an element of k power n plus 1. There are n plus 1 entries. So what are the equations? The first equation looks like, so sigma 1 alpha 1 times beta 1, sigma 1 alpha 2 times beta 2, sigma 1 alpha 3 times beta 3, sigma 1 alpha n plus 1 times beta n plus 1. But beta 2 onwards everything is 0. So we just have beta 1 times sigma 1 alpha 1 equal to 0, right? But then, sorry, so actually I don't want to call them beta i's, I don't want to change the notation in my notes. I will call them A. So A1, A2 up to AR, and A1 is non-zero, A2 is non-zero, AR is non-zero. Okay. So the first equation will be A1 times, so this you can put A1 here, A2 here, An plus 1 here, right? So A1 times sigma alpha 1, A2 times sigma 1 alpha 2, but A2 onwards everything is 0. So this is what we have. But note that since alpha 1 through alpha n plus 1 are linearly independent, alpha 1 must be non-zero in particular, right? Any linear independent set cannot contain a 0 vector. So alpha 1 is non-zero, and hence sigma 1 alpha 1 is non-zero. Sigma 1 being a field homomorphism, it must send non-zero elements to non-zero elements. So that means A1 is 0. But that's a contradiction, because we are taking a non-trivial solution, and if A2 onwards everything is 0, A1 better be non-zero. So this is absurd. So we can assume R is at least 2. So again, to recall, the setup is we consider a homogeneous system of equations where the number of equations is strictly less than the number of variables, and hence we are guaranteed that there is a non-trivial solution, and among all the solutions we are picking one which has the least number of non-zero entries, and that R, which is the number of non-zero entries, is at least 2 is what I just, if R is 1 we are done. So we are now going to assume R is at least 2. So now let's get into the proof, really the heart of the proof. So I am going to rewrite the equations just for clarity. Look like this. The equations look like this. Okay, so the previous slide contains the matrix, but I want to write it directly as equations. So the equations look like this. A1 sigma 1 alpha 1 plus A2. So I am just going to replace the variables by AIs, because that's a solution. This is a solution, right? So that means A1 times sigma 1 alpha 1, A2 times sigma 1, remember sigma 1 is fixed, sigma 1 alpha 2 plus AN, or so here is where I am going to use the fact that everything after AR is 0. So I am going to stop with AR. So AR minus 1 sigma 1 alpha R minus 1 plus AR sigma 1 alpha R is 0, right. So the point is, note that we don't have any terms after the rth term, right, because this is because AR plus 1 and up to AN plus 1 are all 0. So if this is R, everything below that is 0. So I don't need to write this later part of this. So beyond the rth column, so if this is the rth column, anything beyond that is not going to contribute to the equations. So I'll stop with this. So the second equation, just so that I am going to write this just for your clarity. So I have sigma 2 is fixed in this row. So sigma 2 alpha 1, A2 sigma 2 alpha 2 plus, I am going to write these terms because it will become clear what we do later, sigma alpha R minus 1, AR sigma 2 alpha R. Okay. So now, actually I should have said this here. I want to make a further simplification. Since AR is non-zero, so the last non-zero entry in the solution, we can multiply by AR inverse and assume AR equal to 1. Okay. So we can multiply by AR inverse and assume that AR equal to 1. That is because every time you have a solution, if you multiply by non-zero, if you have a solution to a homogeneous linear system of equations, multiply the solution by a non-zero scalar, what you get is still a solution. So multiplying by AR inverse, we can assume that AR equal to 1. So I am going to skip that. Okay. So that is what that is a simplification. So I have simply sigma 1 alpha R sigma 2 alpha r equal to 0. Okay, and the last equation, so I have written first, second, the last equation will be a1 sigma n alpha 1, a2 sigma n alpha 2, ar minus 1 sigma n alpha r minus 1, and ar is 1, so sigma n alpha r equals 0. So let's call this star. So star is the original set of equations applied, very written in terms of the solution that we have chosen, a1 through ar, which is the least number of non-zero entries. So just to give you an update about what we will do later, we are going to construct a solution with fewer non-zero entries and thereby getting a contradiction. Okay, so this is the equations after you plug in the solution for the variables. Now I am going to observe a few things here. So if, and just also recall that we have so far not used the fact that sigma i's form a group, and this is the first place now we are going to use that. So the point is, so I am going to write it here, since sigma 1 through sigma n is a group of automorphisms of K, one of them is identity map. One of them is identity. Let us say sigma 2 is identity, just for simplicity. If sigma 2 is identity, what is the second equation going to look like? A1 alpha 1, A2 alpha 2, sigma 2 is identity, right? So sigma 2 alpha r minus 1 is alpha r minus 1, AR minus 1 alpha r minus 1 plus alpha r equal to 0. So second equation will look like this. But now remember, alpha 1 through alpha r are independent, right? Alpha 1 through alpha n plus 1 are independent, but this is a linear relation that is non-trivial. Linear relation among, because alpha r has appeared with coefficient 1. In fact, all of them are non-zero, right? A1 through AR. So this is a non-trivial relation among this, but we know alpha 1 through alpha n plus 1 are linearly independent. So that means what? I should have said that this is a non-trivial relation. Yeah, so I should write if AI is in F for all I. Otherwise, that is not a relation, a non-trivial relation among this over F, right? They are linearly independent over F. So if they are not in F, there is no problem, but because they are linearly independent over F, they can't have a linear relation, non-trivial linear relation with coefficients in F. So if all the AIs are in F, we do get a non-trivial relation among all of them. So hence, not all AIs can be in F, right? So at least one AI is not in F. So I am going to simply assume, without loss of generality, assume that A1 is not in F. So A1 is in K, of course, but not in F. Okay, so just a word about why I can choose it to be A1. We know that A1, A2, R minus 1, one of them is not in F, because if they are all in F, we get a contradiction to the linear independence of alpha i's over F, capital F. Okay, so one of them is not in F. If A2 is not in F, I am just going to interchange and call that A1, I will call A1 A2. So there is no problem. So just for simplicity, I am going to assume that A1 is not in F. Now this is the first point where we use that they form a group. In fact, we have not used the full force of the group axioms. We have just used that there is identity. But remember, this is not enough, because in the example of k equal to q adjoint root 2 comma I and s equal to 1 sigma 2 that I mentioned in the previous video, k power s is actually k colon k power s is 4, because k power s is q. So here also there is identity, but still the equality doesn't hold. So we have to use more group axioms later on. Nevertheless, let us just assume that for now that A1 is not in F. But if so, A1 is not in the fixed field, right? A1 is not in the fixed field. So that means sigma i's of A1 is not equal, they are not all the same elements. So in particular, one of the elements is identity. So there exists an index k among the n homomorphisms such that sigma k of A1 is not equal to A1, right? Because if this is true, this must be the case, because otherwise it must be in the fixed field. So if sigma k A1 is equal to A1 for every k, that means A1 is fixed by all the group elements sigma 1 through sigma n. So there is at least one k such that sigma k A1 is not equal to A1. Okay, this, you think about this. If sigma k A1 equal to A1 for all k, or let me write it like this, sigma I equals A1 equals A1 for all I, then AI1 is in the fixed field. So that's really what I'm saying. So if that is the case, then A1 will be in the fixed field, which we know is not the case. That means sigma k A1 is not equal to A1 for some k. I'm going to fix that k. And now the clever thing that we'll do is apply sigma k to all equations in star. So star is this. So apply sigma k to this. So unfortunately I have to go down and write this, but you can pause the video and go back, and I suggest that you take a paper and pen and write all this down and apply sigma k to this. Okay, so I'm going to maybe instead of writing all the equations separately, just combine them like this. What is the equations? Star can be captured by this. Star is actually sigma j alpha 1. So I'm going to write j varies over 1 to n. Okay, so j varies over 1 to n. So I get sigma j a1, rather I get a j. See, remember a1 alpha 1, a1 alpha 1, a1 alpha 1, a2 alpha 2, a2 alpha, sorry, so ai, yeah, so I should write this as a1 sigma j alpha 1 plus a2 sigma j. Okay, so let me just get this correct so that I don't make a mistake. So I get a1 sigma j alpha 1 plus a2 sigma j alpha 2, ar minus 1th term will be ar minus 1 sigma j, sorry I skipped something here, sigma j alpha 2 plus a r minus 1 sigma j alpha r minus 1 plus sigma j alpha r equal to 0 for all, right. So I'm just trying to write all the equations in a single line. So you vary j equal to 1 to n, you get all the equations. When you put j equal to 1, you get the first equation. You get a1 sigma 1 alpha 1, a2 sigma 1 alpha 2, a r minus 1 sigma 1 alpha r minus 1, which is this, and finally sigma 1 alpha r. If you take j equal to 2, you get the second equation, a1 sigma 2 alpha 1, a2 sigma 2 alpha 2, a r minus 1 sigma 2 alpha r minus 1, sigma 2 alpha r, which is the last term. If you take j equal to n, you get the last equation, right? So this is just a convenient way of writing all the equations. Now you apply sigma k to these equations, these n equations. So I am going to go over 30 minutes for this video, but I want to finish this so that this will become a self-contained video to prove this theorem. So if you apply sigma k to this, now I am going to call that star star. This looks like this. Sigma k is that fixed k. Remember that fixed k which has this property. Sigma k A1. Sigma k is a group field automorphism, right? So sigma k of this will be sigma k of A1 times sigma k sigma j of alpha 1. So that is just composition. This is composition. Second term will be sigma k A2, sigma k sigma j alpha 2. R minus 1th term will be sigma k A r minus 1, sigma k sigma j alpha r minus 1, and finally sigma k sigma j alpha r equal to 0. Again this holds for all j between 1 to n. So j equal to 1, you get alpha. If you apply sigma k to the first equation, j equal to 2, you apply sigma k to the second equation, and so on. So this is again a compact way of writing really n distinct equations. So I hope this is not becoming too complex, too messy for you, but if needed, please stop and think about what we are doing here. So we have now these equations. Okay. Now this is where we are going to use the fact that this is a group. Earlier we used that there is identity, but now we are going to use more axioms of group. So when you take a group, this is some standard thing that you've heard in group theory. If you take a group and multiply all the elements by a single group element, namely sigma 1 in our case, is a permutation of this, right? So if you take a group and you multiply all group elements by a fixed element, you just get the same group. I mean, they are all group elements, but in a different order perhaps. So for example, if you take the Klein 4 group, okay, so this is an example. Multiply everything by A, so you get A times 1, A times A times B, A times AB, but this is A, this is 1, this is AB, and this is B. So this is just a permutation of the group, right? So in general, sigma k sigma I equal sigma k sigma j implies this is if and only if sigma I equal sigma j. This is the feature of the group, because if that is happens, then cancel by sigma, multiply by sigma k inverse on the left, you get this, and if this happens, multiply by sigma k on the left to get this. So this is just a permutation of sigma i's. In other words, if you look at star star, sigma k sigma j is some other sigma j. As you vary k, you get all the group elements. So this explaining here, you have, let's say, 10 elements, sigma 1, sigma 2, sigma 10, and k is 5. So multiply sigma 1, the first equation, by sigma 5. So sigma 5 sigma 1, second equation will be sigma 5 sigma 2, 10th equation will be sigma 5 sigma 10, but sigma 5 sigma 1 will be sigma 6, let's say. So it will be sigma 6, and sigma 6 will never appear again in the 10 equations. Sigma 5 sigma 2 will be sigma something else, not sigma 6. It may be sigma 8. So sigma 8 will be there. It will not appear again. Third will be sigma 2 maybe, and the last one will be the missing sigma I. So when really what we have done by multiplying by sigma is sort of interchange the equations, but the first entry will be different because you are taking sigma k a1. So this star star becomes, so basically the upshot is that I don't need to really talk about sigma k sigma j. So star star becomes triple star, which looks like this. So star star star, it will be sigma k a1 but sigma k, sigma j, I replace by I. Okay, so original order is replaced by a different order. If you just look at these terms, if you look at this term, I am not touching the sigma k a1, those terms. This will be sigma I alpha 1 plus sigma k a2, sigma I alpha 2, r minus 1th term will be sigma k ar minus 1 times sigma I alpha r minus 1, and the last term will be sigma I alpha r equal to 0, where I goes from, so i's are again going from 1 to n, like j's are going from 1 to n, but it's possibly a different order. So I hope this is the really somewhat tricky part, but I hope this is clear. So we are taking sigma k, sigma j, but sigma k, sigma j is just another ordering of the group elements. So I am just using a different letter for the index. So we have this, and now I'm going to subtract star minus star star star, single star minus triple star. If I do that, what do I get? So star was all the way here. So star, maybe I'll write star just for in this compact fashion so that it becomes clear. Star is really a1 sigma I alpha 1, a2 sigma I alpha 2, a r minus 1 sigma I alpha r minus 1 plus sigma I alpha r minus alpha r, right. So this is star, a1 sigma I, a2 sigma I, index subscript of a and alpha are same, a1 alpha 1, a2 alpha 2, ar minus 1 alpha r minus 1, ar alpha r, but ar is 1. So subscript of a and alpha are same. The first equation has sigma 1, second equation has sigma 2, third equation has sigma 3, nth equation has sigma n. So sigma I. So again I goes from 1 to n for both of these. So now you do star minus triple star. So if you do star minus triple star, we are almost done. So we are getting there. So if you do that, again I am going to write the compact form. So the first column will have sigma, the first equation will have sigma 1, sigma k a1, sigma 1. Here it will be a1, sigma 1, alpha 1. So it will be a1 minus sigma k a1 times sigma I alpha 1, right. So sigma I alpha 1 is common. So you remove that and write sigma k a1 or a1 minus sigma k a1, because you are doing star minus star star star. The second term will be a2 minus sigma k a2 sigma I alpha 2, right, plus dot dot dot, r minus 1th term will be a r minus 1 minus sigma k a r minus 1 sigma I alpha r minus 1, and this is the way that we have arranged this. The last terms will go away, right, because sigma I alpha r, sigma I alpha r, plus there is nothing basically. So that is equal to 0. Now again this is for all I from 1 to n. So again I invite you to just write down all of them if needed. There are n equations. Now stare at this carefully. Now what we get is, we conclude a new equation, new solution to the, a new solution to the original system. What is the new solution? New solution has only r minus 1 terms now. This is the first coordinate. of the new solution. This is the second coordinate of the solution. This is r minus first coordinate, right? Because if you plug this in the column vector corresponding to the variables, you get exactly the solution, right? Because sigma I alpha 1, sigma I alpha 2, sigma I alpha n plus 1 is the row in any particular row. So when you multiply that with this entry, this vector, you get the solution. So that means solution is a1 minus sigma k a1, a2 minus sigma k a2, all the way up to ar minus 1 minus sigma k ar minus 1, comma 0 0 0. So this is a solution to the original system. Moreover, a1 minus sigma k a1 is non-zero, right? That we assumed. That is how we chose k. So the first entry is non-zero. So that means this is a non-trivial solution which has at most r minus 1 non-zero entries, right? Because this is 1, first one, second one, r minus first one. So there is at most r minus 1, maybe even this is 0, I don't care, but it cannot have more than r minus 1 non-zero entries. This contradicts because remember, and r was chosen so that you have the least number of non-zero entries in any solution is r. Okay, if you don't like this contradiction method, what you can really interpret what we have done is, you take any solution, non-trivial solution. Okay, take any non-trivial solution. So another approach, take any non-zero solution, repeat the above process to get another solution take any non-trivial solution and repeat the above process to get another solution with fewer non-zero entries, right? Another interpretation of this is, we originally started with a solution with r entries, right? R non-zero entries, these are all 0 entries. So this is n plus 1 minus r 0 entries. We started with a solution with r positive non-zero entries and ended up with r minus 1 non-zero entries, or less in fact. So we can always start with, maybe there are 100 non-zero entries. Repeat this process to get it down to 99. Repeat it again to get it down to 98, and keep all the way to get it to 1. And once it's 1, we get a contradiction directly. Okay, so that's another way to read this proof. So take any solution which is non-trivial, repeat the above process of rearranging equations, applying sigma k and so on to get a solution with fewer non-zero entries, and repeat it. Because it's a finite vector, eventually you will get one non-zero entry, and which will give you the contradiction. So the proof is complete, right? Theorem 1 talked about some lower bound on the degree of the field over the fixed field. Theorem 2, if you assume that they form a group, then it gives you an exact equality. So these two statements are critical for us. We will repeatedly use them throughout the course, and the proofs are beautiful. So please make sure that you understand the proof, and if you have any questions, please feel free to ask doubts, but really there is nothing more than elementary linear algebra here. So I hope you carefully follow this and work it out yourself if needed to understand the proof. So let me stop this video here, and in the next video we are going to now make use of these very important theorems and study Galois theory. Thank you.